We notice that in a periodic table, as we move from left to right across a period, or we move from top to bottom in a group, we notice a pattern in change in properties of the elements. As in, we notice a change in valency, we notice a change in valence number, in chemical reactivity, in size of atoms, and everywhere we see a pattern. So in this video, we are going to learn about the pattern of change across a period and also down the group. Let us first talk about the trends that we notice along a period in the following properties. So we will start with the first property, that is valence electron. Now we see that on moving from left to right in a period, number of valence electrons increases from 1 to 8. So let us take, for example, any period. Let's talk about the first period. So first period is an exception where we have only two elements, hydrogen and helium, and the last element has only two valence electrons. So the first period is the only exception where the valence electron increases from 1 to 2. Other than that, you pick up any other period. For example, this is the third period. And in the third period, the first element is sodium. So if I write its configuration, it will be 281. Magnesium would be 282. Aluminium would be 283. Silicon would be 284, and so on. And argon would be 288. So we see that the number of valence electron is increasing from 1 to 8. Atomic number. On moving from left to right, we observe that elements have consecutive atomic numbers. So if you look at this, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, so they are consecutive numbers. So in any period, the atomic numbers are consecutive numbers. Valency. On moving from left to right, valency starts from 1, increases to 4, and then decreases to 0. Now that is interesting. Let us take a look. So if we talk about sodium, what is the valency? In order to understand valency, let us first write their electronic configuration. Sodium is 281, magnesium is 282, aluminium is 283, 284, 285, 286, 287, 288. Right? So now here it's for sodium, it has one valence electron. So in order to be stable, what would sodium like to do? It would like to release this one electron. Correct? So that means valency of sodium is +1 because it just wants to release one electron. What about magnesium? It wants to release 2 electrons. So the valency is +2. Aluminium wants to release 3 electrons. Silicon wants to release 4 electrons. Phosphorus wants to release 5 electron. Is that right? No, because releasing 5 electron is a big deal. It would involve a lot of energy. Easier way for phosphorus is to accept 3 electrons. Right? Accepting 3 electrons is easier in terms of energy when compared to releasing 5 electrons. So therefore, here for phosphorus, the valency would be -3. Similarly for sulfur, releasing 6 electrons is easy, or accepting 2 electrons. So accepting 2 electrons is easy. Similarly for chlorine, accepting 1 electron is easy. For argon, it is already in a stable state. So it neither wants to lose nor wants to gain electrons. So what do you see? Valency starts from 1, increases to 4, and then again decreases to 0. And that is the trend seen across all periods. Next, atomic size. On moving from left to right, atomic size decreases. Now you may ask why. Why atomic size decreases? Because if we look at the electronic configuration, what do we see? We see that each of these elements in a period, all of them have 3 shells. Correct? All the elements, they will have 3 shells, K, L and M. But then why is the atomic size decreasing? That is because we see that as we move from left to right, the number of valence electrons are increasing. For example, if there are 3 shells like this, 1, 2 and 3, in the outermost shell for sodium there is 1 electron. But when it comes to magnesium, it has 2 electrons. When it comes to aluminium, it has 3 electrons. So basically we see that as we go from left to right, the number of electrons in the valence shell is increasing. Therefore, but what happens is, as the atomic number increases, the number of protons in the nucleus also increases. Right? So here the number of protons, the number of positive charge also increases. Therefore, the power to attract the negatively charged electrons also increase. As a result, the size shrinks. So what happens here is, the number of shells are the same, but with increase in atomic number, you have more positive charge in the nucleus. Therefore, you have more power to attract the electrons. As a result, overall the size shrinks and therefore atomic size decreases. Let's talk about metallic character. Metallic character is defined by the tendency to lose electrons, right? So as we move from left to right, we see that metallic character decreases. That means the tendency to lose electrons decreases. How? Let us again look at the number of valence electrons. So if you, now I'm not going to write the configuration again and again. Number of valence electrons increases from 1 to 8. Right? Now here for sodium, it has 1 electron, very easy to lose electron. So the tendency to lose electron is very high, right? So it has high metallic character. For magnesium also, okay, it is okay to lose electron. Aluminium okay to lose 3 electrons. Silicon also okay to lose 3 electron, but phosphorus is not okay to lose electron. Sulfur is all the more not ready to lose electron. Chlorine all the more not ready, and argon is definitely not going to lose any electron. So we see that the tendency to lose electron is decreasing. So we can say that tendency to lose electron decreases from left to right. So we can say that the metallic character decreases from left to right. And what happens to non-metallic character? Non-metallic character is just the opposite. Tendency to gain electron. So tendency to gain electron will increase as we move from left to right. Therefore, non-metallic character will increase as we move from left to right. So tendency to lose electron will decrease from left to right, and tendency to gain electron will increase from left to right. Now we talk about chemical reactivity. What happens to chemical reactivity? On moving from left to right, chemical reactivity first decreases and then increases. How? That's because, again, let's talk about the valence electrons. So this is how we have the valence electrons. What happens to the reactivity? So initially the chemical reactivity is quite high for sodium because it has 1 valence electron, very loosely bound, very easy to lose that electron, and that's how it reacts with other substances. So chemical reactivity is quite high. But as we go towards the right side, we see that magnesium has 2 electrons. So losing 2 electrons is little more difficult than losing 1 electron. Losing 3 electrons little more difficult. 4 electrons more difficult, right? So therefore the reactivity will gradually become lesser, right, as we move towards the right side. But then what happens again after this? So if we talk about phosphorus, it has 5 electrons. So it has to gain 3 more electrons, which is difficult. But as we move towards sulfur, it needs only 2 more electrons. So it is again easier to get 2 electrons. Again, as we go to chlorine, it needs just 1 electron. So very easily it will get that 1 electron. So here again the reactivity is very high. So we see that initially it was high, then it gradually reduced, and then again it gradually increased. What happened to argon? So argon doesn't react at all. So it is completely unreactive. Why? Because it has fully filled outermost shell. So it is already in that stable state. It doesn't want to lose electron. It doesn't want to gain electron. Therefore, it doesn't react at all. So forget about the last group 18. But other than that, we see that the reactivity first decreases and then increases again. Next, we talk about nature of oxides. On moving from left to right, basic nature of oxides decreases and acidic nature of oxide increases. How? So we learned that metallic character decreases from left to right. So metallic character from left to right decreases. Now metallic character is what? So metallic oxides are basic in nature. right? So basic oxides also the basic nature of oxides also decreases, whereas non-metallic character increases, therefore the acidic nature of oxides also increases, because we have learnt this, that metal oxides are basic in nature, non-metallic oxides are acidic in nature. In fact, we have proved that with various reactions as well, right? So these are the trends that we notice in across a period in a periodic table. So let's do a quick summary of whatever we learned so far. We learned that on moving from left to right in a periodic table, valence electron increases, atomic number increases by 1, valency increases from 1 to 4 and then decreases to 0, size of atoms decreases, metallic character decreases, chemical reactivity first decreases then increases, nature of oxides, basic nature decreases, acidic nature increases. So that was a summary of all the trends that we learned so far. In the periodic table, we see that there are a total of 18 groups. However, right now in this class, we will learn only about group 1, 2 and 13, 14, 15, 16, 17 and 18. However, as you go to your higher classes, you will also learn about the other groups. Just like periods, in a group, we see that as we move from top to down in a group, we notice a change in pattern in the properties of elements like valency, atomic size, chemical reactivity, metallic character, and so on. So let's get started. It's time to look at the trends down the group. So we start with valence electrons. All elements in a group has same number of valence electrons. Now that's very obvious, because when you let's just pick up any one group from here. So let us suppose we pick up this particular group. So here, if we start writing the electronic configuration, what do we see? So we see that this is how the configuration would be: 2, 7, 2, 8, 7, 2, 8, 8, 2, 8, 18, 7, and so on. So everywhere we see that the number of valence electron is the same. Next is valency. Now since valence electrons are the same, therefore the valency is also same. Atomic size increases as we go down the group. That's because the number of shells increases. For example, for fluorine it is 2, 7. So it has first shell 2 electrons, second shell 7 electrons. For chlorine it is 2, 8, 7. That means first shell 2, second shell 3 is 8 and the third shell has 7. For bromine, it is again 2, 8, 18, 7. That means first shell has 2, then 8, then 18 and then 7. So as we go down, we see that the number of shells are increasing, which obviously means that the atomic size would increase. Next, metallic character. So metallic character increases down the group, but non-metallic character decreases down the group. Now why is it so? As we go down, the size of atom increases. Therefore, the force of attraction between nucleus and the electrons decreases. Right? Because as we go down, what is happening? Here in lithium, if the valence electron was here, so in sodium, what happens? The valence electron is here. In potassium, the valence electron is here. So what is happening? As we go down, we see that the valence electron is going far away from the nucleus. So that means as we go down, the valence electron is kind of not very tightly held by the nucleus. As a result, the chances of losing the valence electron is high. So as we go down, the tendency to lose electron increases. That means the metallic character increases. So therefore, as we go down, metallic character increases and obviously the non-metallic character decreases. Chemical reactivity. Now on the same logic, we can say that the chemical reactivity increases down the group for metals. Because just now we learnt that as we go down the group, the tendency to lose electron increases. Now when the tendency to lose electron increases, what happens? It tends to combine with other elements to form something. So basically the chemical reactivity is also increasing, right? But here we have a catch, that the chemical reactivity for non-metals decreases down the group. Why is that so? So let's explain. So first we talk about metal. So I think metal part is clear, right? Because in case of metals, the electrons want to go out. Now as we go down the group, the valence electrons are going far away from the positively charged nucleus. Therefore they can go out very easily. Now when we talk about non-metal, what is happening? So in case of non-metal, let's say fluorine, this is the electronic configuration. For chlorine, this is the electronic configuration. If you talk about bromine, this is the electronic configuration, and so on. Now in this case, what is happening? So for fluorine, it is small in size. Therefore, it can attract electrons easily, because end of the day, who has to attract electron? The nucleus, the positively charged protons in the nucleus, right? So since the size is small, so this can easily attract electron from outside, because now the non-metals, they want to gain electron, right? But for chlorine, what is happening? Since the number of shells are more, so now the nucleus will have to put more effort to attract an electron, right? So as we go down the group, the tendency to gain electron decreases, because gaining electrons becomes more difficult as we go down the group. So as a result, as we go down the group, tendency to gain electrons reduces. Therefore, the chemical reactivity of non-metals decreases. Right? So I think this logic is clear, right? Okay. Moving on to nature of oxides. So all elements in a group has same nature of oxides. So there is nothing like acidic or basic, because since they have same number of valence electrons, so that ways, with that logic, the nature of oxides, it doesn't make much difference. So overall, the trends that we observe down the group is somewhat like this. Valence electron same, atomic number increases, valency same, size of atoms increases, metallic character increases, chemical reactivity increases for metals, decreases for non-metals, nature of oxides is the same. This is a quick comparison of the trends for the same properties that we noticed in a period versus we noticed in a group. So this change, whenever we talk about a group, it is from top to bottom. When we talk about a period, it is from left to right. So you see, valence electron increases in a period, it remains same in a group. Atomic number increases by 1, here it increases but not by 1. Valency increases from 1 to 4, then decreases to 0, here it remains the same. Size of atoms decreases, increases, metallic character decreases, increases. Chemical reactivity first decreases, then increases. For groups, it increases for metals and decreases for non-metals. Nature of oxides, basic nature decreases, acidic nature increases, whereas it remains the same in groups. So this was just a quick recap, but I hope that this table could be useful for you for a quick revision. So we noticed that the modern periodic table emerged as a superhero, overcoming all the limitations of the previous versions of periodic table. So needless to say that the modern periodic table was very advantageous, because it made life of chemistry teachers and chemistry students super easy. It also made very convenient to relate properties of a particular element just by knowing its position on the periodic table. Some of the merits of the modern periodic table were: it is based on atomic number, which is a very basic property of an element. This periodic table could explain the reason for change in any property down the group or across a period. It could also accommodate any newly discovered element in the periodic table. There were no anomalies found so far in the periodic table based on the modern periodic law. In fact, chemical bonding also has a link with the periodic table. Let's see how. There also exists a relationship between chemical bonding and periodic table. So we notice that if element from left hand side combines with element from right hand side, they form ionic bond. Now, just a quick recap: when ionic bond forms, when there is transfer of electron, right? Now, elements on the left hand side, they are mostly metals. And elements on the right hand side, they are mostly non-metals. Now metals, they always want to lose electron, and non-metals, they always want to gain electron. So as a result, what happens? There happens transfer of electrons and ionic bond is formed, right? If element from right side combines with elements from right side, they form covalent bond. Now, what is covalent bond? When sharing of electron takes place. Now, if both are non-metals, that means both of these elements, they want to gain electron. Both the elements want to gain electron. So, what do? They share. So, they do not give. So, they say that, okay, I want one electron. You also want one electron. So, let us share one electron. So, I will share one electron with you. You also share one electron with me. So, both of us will have our purpose fulfilled. And that's how covalent bond is formed. Please note that element from left hand side do not combine with element from left hand side, because on the left hand side we have the metals and both of them want to lose electron. Now, since both want to lose electron, transfer of electron cannot take place, sharing cannot take place either. So therefore these elements, they do not combine with each other. So that's the relationship between chemical bonding and periodic table. We can take examples. Let us take examples of sodium and chlorine. So sodium loses one electron and chlorine accepts that one electron. So what is the type of bond between sodium and chlorine? Obviously, this is ionic bond. So we see that a metal which is on the left side of the periodic table combines with a non-metal which is on the right side. If you take the example of carbon dioxide, CO2, what is the type of bond? So here carbon and oxygen both are from the right hand side of the periodic table. But here we see that they share electron. So for example, carbon has 1, 2, 3, 4. Oxygen has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So they share electrons like this. So this is covalent bond. So I guess with this video, you got a very good idea on the arrangement of elements in the periodic table. So if I point out a particular element on the periodic table, I'm pretty sure that you would be able to guess at least few properties of that element, right? If at all you are interested to memorize the periodic table in a very interesting way, here is a link to a very interesting video with a shortcut that will help you to learn the periodic table within 10 minutes. So wondering what are we going to do in the next video? So the next video we are going to talk about few interesting questions based on periodic classification of elements, and that's going to be super interesting. So stay tuned.